2023, a certified laboratory test in Hunan province recorded a compressive strength of 240 megapascals for a graphene-enhanced concrete mix. Let me tell you what that actually means in plain English. Standard high-performance concrete tops out at around 100 megapascals. This material hit more than double that ceiling. The sample did not crack, it deformed. You heard that right. The strongest structural concrete ever certified did not shatter, it bent. That is not a stronger concrete. That is a different category of material entirely, and the craziest part is not the strength. It is that this mix poured like water. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly how a material this strong learned to flow, and why that changes every major construction project on the planet. Concrete is the most consumed manufactured material on Earth. More than 4 billion tons of it are produced every year. And for most of the 20th century, the engineers who worked with it operated inside a constraint so fundamental it stopped being questioned. It became the air inside the room. The constraint was this: you cannot have strength and workability at the same time. Here's what that actually means. When you mix concrete, you are combining cement, aggregate, and water. The water does two things simultaneously. It triggers the chemical reaction that makes concrete harden, and it makes the mixture fluid enough to pour, pump, and place. The problem is that those two functions pull in opposite directions. More water means better flow. Better flow means weaker concrete. The cement paste becomes diluted. The internal structure becomes porous, and porosity is the enemy of compressive strength. Because every tiny void inside a hardened concrete matrix is a point where stress concentrates and where cracks begin. Picture a sponge. Now picture trying to make that sponge bear the load of a 10-story building. The voids that make it flexible are the same voids that make it fail under pressure. That is what a high water-to-cement ratio does to structural concrete at the molecular level. The industry's answer was to minimize water as aggressively as possible. By the 1980s, high-performance concrete programs at institutions like the Norwegian Institute of Technology and MIT's Concrete Sustainability Hub had pushed water-to-cement ratios below 0.3, meaning less than a third of a pound of water for every pound of cement. The result was concrete approaching 100 megapascals. That is roughly the pressure at the bottom of a kilometer of ocean water, bearing down on every square inch of surface. A genuine engineering achievement that took decades to reach. But it came at a cost. Most people who read about this never get to this part. Concrete, that low in water, is brutally difficult to work with. Stiff, unforgiving, demanding specialized pumping equipment and tight environmental controls on every pour. On a large placement, a bridge deck, a dam face, a high-rise core wall, the margin for error is almost nothing. Miss the placement window and the mix starts to set in the pump line. The structural redundancy required to compensate adds material, weight, and cost to every element in the structure. The wall was not a materials problem, it was a physics problem. Every attempt to break both constraints simultaneously ran into the same molecular reality. That was the ceiling, and it held for 100 years. But here's the thing. The team that eventually broke it did not attack the water ratio directly. They went somewhere smaller. The first serious proposals to use graphene as a concrete reinforcement additive started appearing in materials science literature around 2010. The stated goal was straightforward: exploit graphene's extraordinary tensile strength, roughly 200 times that of structural steel by weight, to reinforce the cement matrix at the scale where cracks actually begin. Not at the rebar level, not at the fiber level, at the level of individual crystal bonds forming inside hardening paste. The construction industry's response was measured and not unreasonable. Graphene was expensive. It was difficult to manufacture at scale, and it had a problem that made every other objection feel secondary. Graphene does not mix. Left to itself in a water-cement slurry, graphene platelets clump. They stack on top of each other in dense aggregates, held together by van der Waals forces. The same weak molecular attraction that makes gecko feet stick to glass. A clumped graphene aggregate does almost nothing for concrete strength. You end up with small regions of extremely reinforced material surrounded by a matrix no stronger than what you started with. The reinforcement cancels itself out before the concrete even sets. The objection from established materials bodies was consistent. The dispersion problem made graphene concrete fundamentally unscalable. The American Concrete Institute flagged it in technical reviews. European standards bodies noted the same constraint. The argument was not that graphene lacked strength. The data on that was unambiguous. The argument was that you could not get it evenly distributed through a real mix in a real batching plant at a real construction site. Not a lab, a site. They said the same thing about carbon fiber and aerospace composites. Brittle, expensive, impossible to manufacture at structural scale. We all know how that ended. What the dismissing institutions missed was that a group of researchers working across programs at the University of Exeter, Chongqing University, and several state materials institutes were not trying to disperse raw graphene. They were asking a different question entirely. Not how do we mix graphene into concrete, but how do we make graphene want to stay dispersed? Not forcing it apart mechanically. Changing what it was attracted to at the molecular level. The answer involved transforming the graphene surface before it ever touched a cement particle, and that transformation required a process that sounds, on first hearing, like it belongs in a jewelry workshop rather than a materials laboratory. And the mechanism behind that answer is the part that makes the story genuinely extraordinary, because it sounds almost too simple to work. The dispersion problem came down to surface chemistry. Graphene platelets clump because their surfaces are electrically neutral and hydrophobic. They repel water and attract each other. So the research teams working on this did not try to force them apart mechanically. They changed the surface. Think about what happens when you add dish soap to a pan of greasy water. The grease does not dissolve. In fact, it breaks into tiny droplets that stay suspended because the soap molecule has one end that bonds to grease and one end that bonds to water. The grease is still there. It just cannot find other grease molecules to clump with anymore. That is the conceptual core of what graphene oxide functionalization does to a concrete mix. You attach oxygen-containing chemical groups to the graphene surface, hydroxyl groups, carboxyl groups, epoxide groups, and suddenly the platelet has ends that actively bond to water and to cement particles. It does not clump, it integrates. The process used to attach those groups is called sonication-assisted oxidation. A graphene slurry is exposed to high-frequency ultrasonic waves, the same basic physics as an ultrasonic jewelry cleaner, running at intensities that physically shear apart platelet aggregates while chemical treatment locks the surface groups in place. It is not a delicate process. It is closer to controlled violence at the nanoscale. Here's the part nobody covers. Once the graphene platelets are functionalized and properly dispersed through a cement matrix, they do not just add tensile strength. They change how the concrete fails. Conventional concrete fails in a single catastrophic event. A crack initiates at a void or a weak bond, propagates through the matrix, and the structure loses integrity faster than any warning system can respond. Graphene-reinforced concrete fails differently. The platelets bridge across nascent cracks. They hold the two faces of a forming fracture together, absorbing energy, forcing the crack to deflect around the platelet rather than propagate through. The material does not shatter. It resists. Then it resists some more. Pilot testing at Chongqing University documented compressive strength gains of between 30 and 46% at graphene oxide loadings of just 0.03 to 0.06% by weight of cement, less than 1 part in 1,000 by weight. That is not reinforcement in any conventional sense of the word. That is a molecular restructuring of how the material distributes and absorbs stress. The dispersion problem was solved. The ceiling had its first real crack, but solving dispersion created a problem nobody had planned for. When you functionalize graphene oxide and disperse it properly through a cement slurry, the surface chemistry that makes it bond so well to cement particles also makes the mix stiffer. The same oxygen groups that prevent clumping increase the internal friction between particles in the wet mix. Workability drops, flow drops, and a concrete mix that cannot flow cannot be placed. Not in a real pour, not at real scale, not without crews manually working the material into every corner of the formwork, which introduces the very inconsistency the whole program was designed to eliminate. Measured against standard slump tests, the industry's basic field measure of workability, where a cone of fresh mix is lifted and the resulting spread is recorded. Graphene oxide additions at the target loading percentages reduce slump values by between 15 and 30% compared to control mixes. That is not a minor inconvenience. That is the difference between a mix that pumps cleanly through 300 feet of line to a high-rise deck and a mix that blocks the pump halfway up and sets in place before it can be placed. Here is what most people get wrong about the strength-workability trade-off. The conventional fix was chemical plasticizers, superplasticizers, water reducers, compounds that coat cement particles and reduce friction without adding bulk water. The problem was that standard superplasticizer chemistry was tuned for plain cement mixes. Add it to a graphene oxide slurry, and it competed directly with the oxygen surface groups for bonding sites on the cement particles. In some test configurations, it stripped the functionalization partially off the graphene, causing reagglomeration. You fixed the flow and broke the dispersion. The strength gain disappeared. The solution that emerged from joint testing between Donghua University and a state-affiliated materials engineering program sounds like it should not work, and that is exactly why it does. Instead of adding a plasticizer after graphene dispersion, they co-processed the graphene oxide with a polycarboxylate ether. Superplasticizer during the sonication stage itself, chemically binding the flow-enhancing compound directly to the graphene surface before the mix ever touched cement. The graphene arrived at the mixer already carrying its own lubrication layer. Dispersion held, flow recovered, compressive strength gains were preserved at 41% above control in independent testing at certified load frames. That is not a workaround, that is a materials architecture, but a result at lab scale and a result at pore scale are two entirely different animals, and the gap between them nearly swallowed the whole program. A laboratory specimen is a cylinder roughly 4 inches across and 8 inches tall. It is mixed in a controlled environment, cured at a fixed temperature, and tested under a calibrated load frame by a technician who has run the procedure hundreds of times. A construction pour is a transit mixer carrying 8 cubic yards of material, a pump line running to a deck 60 feet in the air, and a crew working against an ambient temperature that may have shifted 15 degrees since the batch left the plant. Those two environments do not produce the same result from the same mix design. Every materials engineer knows this. It is where promising laboratory programs go to die. Here's where the story really begins. The co-process system worked in a test cylinder. Making it work in a transit mixer required solving a problem the lab stage never identified. Graphene oxide, unlike conventional cement additives, is sensitive to shear history. The longer it spends tumbling inside a rotating drum mixer, the more the platelet structure degrades. Sonication-assisted dispersion produces a specific platelet geometry optimized for crack bridging. Too much additional mechanical shear in the drum, and you start breaking platelets into fragments too small to bridge anything. Still dispersed, just not reinforcing anymore. The old batching approach. Add all components at the plant, mix to standard revolutions, deliver, destroyed a measurable fraction of the graphene structural contribution before the truck reached the site. Testing by the research consortium found platelet integrity degradation of between 12 and 22% for standard drum mixing cycles at full load. The new protocol inverted the sequence. Graphene oxide slurry was injected at a controlled rate into the drum during the final mixing stage, after the cement and aggregate had already been combined and partially hydrated. Injection timing, drum speed, and slurry concentration were managed through a real-time monitoring system fitted to the mixer drum that tracked viscosity changes and flagged deviation from target flow parameters. Think of it as a navigation system for the mix itself, continuously reading where the material is, comparing it to where it needs to be, and adjusting the injection rate to compensate. This is the detail that almost never makes it into the public reporting on this program. The delivery window for the finished mix was fixed at 70 minutes from final injection to placement completion. Miss that window and both flow and bond strength drop simultaneously. 70 minutes is not generous. 31 construction projects across 6 provinces adopted the protocol between 2020 and 2023. The combined result of both mechanisms deployed at field scale produced a certified number that the lead research team required a second independent verification before they would publish it. Here's the honest picture. Graphene concrete, at the performance levels documented in this program, costs between 18 and 30% more per cubic yard than the high-performance conventional mix it replaces. The graphene oxide supply chain, sonication equipment, functionalization chemistry, co-processing infrastructure, does not exist at every batching plant. It requires capital investment, operator retraining, and a quality control discipline that some construction environments cannot yet fully support. Those are real constraints. They matter for adoption timelines. Anyone who tells you this replaces conventional concrete everywhere tomorrow is not being straight with you. Now here is what the certified result actually showed. Independent verification, conducted by the China Academy of Building Research and cross-checked against load frame testing at Tongji University, confirmed a sustained compressive strength of 240 megapascals across multiple pour batches produced under field conditions, not laboratory conditions. Field conditions. That figure represents a verified breach of a ceiling that the global construction engineering community had treated as physically fixed for 4 decades. To put that in terms you can hold in your head, a conventional reinforced concrete column designed to carry the load of a 30-story building requires a cross-section of roughly 24 inches square. A column cast from this mix carrying the same load requires a cross-section of 14 inches square. That is not a marginal improvement. That is 40% of the material removed from the structure without surrendering a single pound of load capacity. 40% less cement, 40% less aggregate, 40% less weight, transferred to the foundation. The secondary figure is the one that restructures the carbon calculation entirely. Cement production accounts for approximately 8% of global carbon dioxide emissions. A 40% reduction in cement content per structural element, applied at meaningful adoption scale, does not improve the construction industry's carbon profile. It rewrites it. Satellite imaging of the 31 project sites, reviewed by an independent structural monitoring program, showed 0 anomalous settlement or cracking signatures across a 30-month observation window. The material performed in the field exactly as the certified testing predicted. That is not a promising material. That is a proven one. If that number surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what happens when this reaches the infrastructure programs that need it most. The question now is not whether graphene concrete works. The question is what happens to the global construction industry when it scales. Every year, the global construction industry pours an amount of concrete that, laid flat, would cover the entire state of California to a depth of more than 2 feet. According to the Global Cement and Concrete Association, that single material generates more carbon dioxide than the entire aviation industry, the entire shipping industry, and all of global aluminum production combined. The infrastructure backlog that concrete is being asked to fill, bridges, tunnels, coastal barriers, urban foundations in subsidence-prone regions, is not shrinking. The United Nations Environment Program estimates that by 2050, the world will add the equivalent of another New York City to its built environment every single month for the next 30 years. And for most of those applications, conventional concrete is already being pushed to its performance limits. Here's the detail that most analysts miss entirely. The real competitive advantage embedded in this protocol is not the graphene. Graphene oxide is a traded commodity. Any materials program with access to the published research can acquire it. The advantage is the co-processing architecture, the specific sequence of sonication parameters, injection timing, drum speed protocols, and viscosity monitoring thresholds developed across 3 years of field-scale iteration. That knowledge is not in any patent. It lives in the operational memory of the teams that ran 31 pours and adjusted the protocol each time. Replicating the certified result requires replicating that process knowledge. That takes years, not months. The sectors where this changes the engineering calculus first are not the obvious ones, not skyscrapers. Those projects already use high-performance mixes and have the procurement sophistication to adopt new materials. The sectors that move first are marine infrastructure, seawalls, harbor piles, offshore platform foundations, where conventional concrete degrades through chloride penetration in under 50 years. And transport tunnels, where the reduction in structural cross-section translates directly into excavation volume and therefore project viability. A 14-inch column instead of a 24-inch column is a footnote in a high-rise. In a bored tunnel beneath a city, it is the difference between a project that pencils out and one that never gets funded. The American Society of Civil Engineers flagged advanced cementitious composites, including graphene-enhanced mixes, as a priority materials category in its 2023 infrastructure research agenda. The path from research priority to adopted standard typically runs a decade in construction. Carbon fiber reinforced polymers were categorized as experimental in aerospace in 1965. By 1985, they were load-bearing on commercial aircraft. 20 years from impossible to structural. The limit here was never financial, it was always technical. And what that limit being broken actually means for the world is the part that takes a moment to fully land. Every major structure built in the last century was sized for a material ceiling that no longer exists. The bridges, the tunnels, the coastal defenses, the urban foundations holding up cities built on clay and fill. All of them were designed for a world where concrete had a fixed performance envelope, and the only answer to its limits was to use more of it. More material, more cement, more carbon, more weight pressing down into foundations made of the same constrained material. What graphene concrete proved, not in a laboratory, not in a simulation, but in 31 field pours at real construction sites, is that the envelope was not a law of physics. It was a limit of chemistry. And chemistry, unlike physics, can be rewritten. If you made it this far, you now understand more about structural concrete and material science than most people who write about it for a living. The world is about to build more infrastructure than at any point in recorded history. The material doing most of that work can now do it at 40% less volume, at more than double the certified strength, with a flow behavior that fits the equipment and crews already on site. That is not a laboratory result waiting for the real world to catch up. The real world already has. 31 times across 6 provinces in conditions no controlled test can fully replicate. What this changes is not just the strength of individual structures, it is the fundamental arithmetic of how much material the built environment requires to carry the loads we keep asking it to hold. Every column thinner, every foundation lighter, every pour producing a structure that will outlast the one it replaced by decades. That arithmetic just shifted permanently. Every ton of cement not poured is a ton of carbon the atmosphere never sees. Now, if this changed how you think about construction materials and what the future of infrastructure actually looks like, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should the construction industry move fast and adopt graphene concrete at scale right now, even if the supply chain and quality control systems are not fully mature yet? Or should it hold the line on conventional methods until the protocol is standardized and the cost premium comes down? Both sides of that argument have real engineering logic behind them.